Hello, I'm Dr. Brian Fraser, and in this demo I'm going to show how to use Pthreads and the Mutex to synchronize processing between the threads. So initially here I've got Eclipse open on the left. I've created a project that's going to build from a makefile, and I'm going to sort of start with this application that I've written here. We can trace it through. We can see here in main I'm going to call this function called counting function, and I'm passing it a single argument. And my counting function simply loops through quite a number of times. Here I think it's 5 million times or 500 million times. It loops through for I equals 0, I less than 500 million, I plus plus. And I'm going to add to my variable sum, which happens to be a global up here, the value that I passed in, which is the argument offset. So offset came in. In this case, offset is 1. So all I'm really doing is I'm going to call this function that adds 1 to the value sum 500 million times. So we're going to expect it to end up with being 500 million. Once that function is completed, we're going to come down here and print it out. I'm using LLD here. That is the format specifier or conversion specifier for a long printed as a decimal. So LLD, and that's so that I can actually print out sum here. I want to use a long so that I can have later on, if I'm doing a lot more counting, we don't have overflow issues. Okay, so let me build that. I'll come over here and just show what the command is. My make command executes. The actual command I'm using currently to build it is this. So you could type that in on the command line if you didn't want to use a makefile, and it would build it for you. So I can run my program, count. It takes a moment to run, and we can see here that the answer comes out as 500 million. Just exactly what we wanted it to do. Okay, so that's the easy thing to do. Let's now kind of start getting into what I want to demonstrate. So this is a single-threaded application. So let's see what happens if, well, let me start off with this. I'm going to time it. So I can type time /count, and this will use the Linux command time to tell me how long it took. So the real time, total time executing was 1 second, 1.19 seconds, so 1.2 seconds basically. So what I'm going to do is I'm going to come down here and I'm going to change this to call it a second time. And I'm going to pass in -1. Rebuild with Control B or Control M in Control B, pardon me, in Eclipse. And then I'm going to come back and re-execute the time command. So we can see here that the sum comes out to 0 because I first counted up by 1. 500 million times, and then I counted down by 1, 500 million times, putting me back exactly at 0. And it took just over 2.5, or just about 2.5 seconds to run. And if I run this a few times, it'll take 2.5 seconds each time approximately, slightly different each time due to scheduling differences. But each time the sum comes out to 0. Because my code is basically correct, right? It does what it should, it accesses the global variable, adds 1, subtracts 1. No problem there at all. Now, let's say we wanted to bring in threads. So with threads, we can put some computation in a background thread or a secondary thread. So I'm going to start by commenting out this counting function second one here. And what we're going to do is we're going to convert our counting function to being a thread function. What that means is simply that this is going to be the function that gets executed when a thread begins processing. So we can come in here and we can say, well, instead of if we look at the prototypes and so forth for Pthreads, you can check out my other videos which will be linked below on setting up Pthreads. We need to return a void star. Instead of us taking in an integer, we need to take in a void star, which is going to be the argument. I still want this offset for the rest of my code, but I need to get that from the arg. Now I've got a pointer to a void, so I need to make that a pointer to an int, because that's what it was being passed in. That'll be a pointer to an int, but then I need to dereference it. So this will take arg, make it a pointer to an int, and then dereference it, which is to say follow the pointer, and give me the value and put that in the offset here. And then offset then just processes as normal, and at the end we need to return a value. So the way that you often exit a thread function is you can call pthread exit and pass some value. I don't need anything, so I'm going to pass in null. Just saying, just exit, I'm not passing anything back. Which is effectively, whatever I pass in here is going to be what's returned by my thread function, effectively. Okay, so a couple other things I need to do. I've started to use threads, so let's actually launch the thread down here. So I'm going to use pthread underscore create. I need to pass in the ID of the thread ID, so I need to create one. So pthread Now let's check that out. So what's it going to be? It's going to be pthread type deft, and let's call this one ID1 just for fun. And here I'm going to pass in a pointer to that. If I hit Control Space, Eclipse tells me that this should really be a pointer to a pthread object. So we're going to have the address of ID1. Next, I need to pass in the attributes. I'm not going to pass any attributes in, so I'm going to pass in null. I need to pick the thread function. So this is currently called counting function. Importantly, I don't want to pass in brackets. I just want the function here. Let me expand Eclipse just a little. And let's minimize that to give ourselves a bit more room. And then finally, I need to pass in an argument. Well, I'd often pass in null if the whole threading function was self-contained, but here I do need to pass in an argument. I need to pass in a pointer to a value. So let's make a value here. Int, and shall we call this one offset 1, why not? Equals 1. And now I need to pass in an address of that. So offset 1. Now it needs to be a void star, but you can cast anything to and from void star quite nicely in C, quite permissively I might say. So that'll do us. So effectively what I'm doing is I'm converting this one line, counting function 1, instead of it being a normal function call, I'm going to switch it to a threading kind of framework. So here I have my code to launch the thread. I've already changed my prototype to handle a thread, so I can get rid of this. Don't need that anymore. And then the last thing I need to do is down here, I'm going to do a Pthread Join, which will force the main thread to wait for the background thread to finish. And I need to pass in, let's see here, we need the pointer to the, we just need the thread ID, so I can pass in ID1. And then I can accept some sort of pointer back. I'm not passing anything back, so I'm going to pass null, or accept null here. That'll tell Pthread Join I don't want anything. Okay, so we're getting there. Now if I try to build this, it's not going to work. I can scroll back through all of my big errors here, and it tells me implicit declaration of pthread exit. Now, this is partly due to I've set to turn on all warnings and turn on treat all warnings as errors. This is a great idea because it forces you to actually get correct code. So what I need to do here, effectively, if it tells me implicit declaration, I'm probably missing an include. So hash include pthread.h. So now if I try building that, it still fails. Let's see why. It says undefined reference to pthread. Now undefined reference, this is actually in the linking phase. So if I scroll back to the left here, it's going to be in the linking phase. It's not showing us anything different here. What I need to do is I need to tell GCC that when it links this together to include the pthread library. So I'm going to come into my make file and I'm going to add the argument -pthread, which adds all of the pthread support. This is a make file to actually build this. I'm saying here I'm building the target count, and I'll save that. Build should function okay. Let's go back to the make the command line here and just show what it's going to look like. So make clean, and then I'll type make. So I'm executing this command to build it. You can see the -p thread here is the extra argument we just added for the build. So now if I run this, so I can do time, for example, .count, we can see that we come up with 500 million, and we're approximately at the same time we were before. If I run this a few times, it's going to have somewhat consistent timing. Maybe it takes slightly longer to run than before, but that's okay. But we're only executing half the problem. We're only currently counting up. Well, if we wanted to also count down, we effectively duplicate the work we just did. So, I'm going to get rid of that call here. What I'm going to do, well, let's just, for fun, start this off. I'm going to take all of this code, duplicate it, change all my IDs from 1s to 2s. If I was trying to do this in general, I'd probably create an array, but I'm just going to use a couple threads here, so that should be fine. So let's double check what I've got here. I'm creating a second thread ID, setting the offset here to be -1, so it's going to try counting down. I'm then going to create a thread using the exact same function, so it's the same threading function, but sort of a different instance of it. So secondary thread. I'm going to then pass in the thread ID and the offset, the new offset I've created, and I'm going to join on it. So this is going to actually have a problem for me. What I'm going to do is I'm going to count all the way up on a thread. I'm going to wait for it to finish. I'm then going to count all the way down and wait for it to finish. So this is really no more efficient, right? I'm just, while my main thread is waiting, a background thread is doing some processing. That's a complete waste of threads. I'm not really exploiting anything, not getting anything from this. So what I'm going to do is I'm going to make it so that I have two basic sections here. I'm going to spawn threads, and then I'm going to wait for threads to finish. Wait for threads to finish. And so to do that, I can move my joins down here. The order is irrelevant for my joins. It'll simply wait for one, then finish waiting for the other. And they should finish approximately the same time. Now the one last thing here I wanted to do before we actually run this is no longer my counting function. I'm going to name this my counting thread. So I do Control or Alt Shift R to rename in Eclipse, and I'm renaming all of these from counting function to counting thread just to make it a little clearer. So save that, come back to my command line, make, and let's do time. Let's start off with just running it. See what happens. Now, interestingly, I'm getting the wrong value here. Let's run with time. The sum is coming up to the wrong answer. We can see, though, that it's not taking a lot longer than it took with a single thread. So up here, when it was doing the single thread, it took 1.2 seconds. Now it's taking 1.7 seconds. I can show you kind of what's going on here. I can run my system monitor. So I went to the Ubuntu Start menu and ran System Monitor. Make it so it fits on the left here. So you can see this is a virtual machine running Ubuntu. I've got 4 processors mapped, CPUs mapped to this virtual machine. When I rerun now, 2 of the threads jump up. They both sort of finish at the same time, but maybe you can just barely see in here that 2 threads have gone sky high instead of 1 thread before. So I'm effectively using 2 threads or 2 processors in parallel. But of course, there is a problem, and that is the fact that my sum is no longer 0. It should be 0 because I've got 1 thread that's counting up at 1, 1 thread that's counting down at -1. So if I run this again, we'll see that it keeps changing back different numbers every time. It seems somewhat random. So this is a race condition, where the order of execution makes a big difference in the actual processing. So, what do we solve this with? Well, we need some way of doing synchronization. We have a critical section problem here. We need to identify what the critical section is, and then fix it with some form of locking mechanism. So, a critical section happens when you have shared data between multiple threads or processes. In this case, I've got multiple threads, and they're all using this variable sum. Everything else is separated. We've got separate instances of our thread function running. We've got separate variables being passed in. We've got local variables used here. The only thing that's shared is sum. So I need to protect access to sum in some form of critical section. So I'm going to say start critical section. Here we do some work, and then I end critical section. So I'm going to use a Pthread mutex for this. It's the simplest form of locking that will ensure mutual exclusion. So, to begin with here, let's set up a Pthread. So I'm going to say Pthread mutex. Let's call it mutex. And I need to initialize it, and there's a handy default initialization which you can use Pthread _ mutex, hit control space here, initialize. So this will create me and this should be a Pthread mutex _ t because it's a type def. Okay, so that will generate me a mutex that I can then work with. Let's compile that. Of course, we haven't done anything with the mutex yet. I need to, in my critical section, lock the mutex, so I can use Pthread mutex lock. Here I pass in, well, let's see what we need to pass in. We can come to a command prompt, type man Pthread mutex lock. And let's just do Pthread mutex. And 3. Nope. Okay. I think you just do Pthread. Yeah, okay. I had gotten it earlier. Anyway, we can check the documentation for that and find it out. So in here, I'll just use Eclipse, Control Space. It wants a pointer to a mutex. So I'm going to pass in here the pointer to my mutex named mutex. It's the address of my mutex. I'm going to duplicate that. The opposite function from lock is unlock. And so now I will unlock my mutex. So all I did is I created a mutex. Before I used the shared resource, I lock the mutex. And then when I'm done using it, I unlock the mutex. This forces all access to these lines of code. In this case, there's only one line of code, but this line of code is then protected by a mutex, meaning only one thread can access or execute this line at once. So let's build that. And over here, I'm going to rerun my time command. So before it took 1.8 seconds. Now it's taking quite a bit longer. Let's switch back to our threads here. We can see that a fair amount of activity is going on the threads. They're going through, doing a lot of processing. We see that they now switched cores here, seeming to take a very, very long time. Now let's check the code here while this runs to see if we screwed anything up. So coming in, I initialize my mutex. So the mutex initializer. Down here, I correctly lock. At the start of my critical section, I call mutex unlock here to unlock it. And we see back here, and whoa, it took 45 seconds. However, it did the sum correctly. So we went from 1 second to 45 seconds just by adding in a mutex lock, which is quite a huge increase. Now what we're really doing here is we're adding 2 system calls in our loop. So that's quite a lot of overhead. So I don't want to go quite so many times through, so I'm going to put this back, so instead of 50, I'm going to switch this back to, let's go to 20 million, just to make it so it runs faster. So I'm now doing a lot less processing here. We're down to 2 seconds on my processing. So now what have I done is I took this parallel function, my threads, and I made it so that they didn't clobber each other. Now you could argue, wait, hang on. I went from a previous solution way back at the top that took 2 seconds or so, and I went up to 45 seconds here. Now if in some cases this wouldn't be a reasonable idea, but if you do need multiple threads for whatever you're doing, and you don't have quite the same level of sort of shared data as I've got here, having those the multiple threads can really improve the computation speed of your process. In this case it doesn't, but it's just a toy example, because I'm doing so many millions, literally, of my mutex lock and unlock. Now, going from here, up here when I had the no locking, my mutex just ran, or no with no mutex, pardon me, to down here with the mutex, the big difference, of course, is that we now have the correct answer. So it really doesn't matter how slow your code is in some cases, as long as you get the right answer. The right answer is the most important thing, and then anything you need to do to get there is, in one sense, a requirement. So, yes, it takes a lot longer, but it is absolutely critical in order to get the right answer. Okay, so that's the big thing I wanted to show with the mutex, the locking and so forth. I want to show a few other things that can really go wrong in terms of accessing threads. So if I come down here, the first thing I wanted to show is, at the moment I'm creating a variable for offset 1 and passing that in here. And I'm creating a new one for offset 2 and passing it in here. So you might be tempted to think, well, what about if I simply use the same value again? So I can say here, offset 1 equals -1. And in here, let me just duplicate that line. I'm going to pass in, instead of offset 1, or 2, I'm going to pass in offset 1. So I'm just reusing this offset 1. So this seems like it might work fine, but realize that we're passing in an address to it, not just the value. We're not passing by value, we're passing by pointer. And when we pass by pointer, that pointer actually comes in here as the address that I'm accepting. I then convert it and pull the value out. So if we execute pthread create, and then this thread starts up and gets control, executes this line of code, does something else, and then after that, we spawn a second thread, we'll have no problem. Because the first thread will have already captured the value of offset into its local variable. But what can often happen is this thread up here, my first thread, does not get spawned or does not get executed before we've actually spawned a second thread. So effectively my main thread comes through, creates one thread, creates a second thread, and then only then do either of the threads begin executing. So let's see what happens when I do this, when I run this code. So if I run my timer here, we see in this case that it came out to negative 40 million, which is because my constant here is 20 million. Now, if I run this a few times, it may not always give me the same answer. Let me speed this up just by making it 10 times faster. Get rid of a 0 there. And let's just run count. Now here it's fairly consistently giving me this value. But sometimes when you run it, depending on the scheduling and other things on the system, like there, it'll give you the value 0. Because in these cases, let's minimize that to give us some space, whenever we get the 0, what is going on is the first thread, we create it, we execute a little of it, we grab into a local variable the value of the offset, and then and only then do we create the second thread. In most cases, however, we create one thread, we create the second thread, and only then do the threads get a chance to execute. By this time, they're accepting the same address, they got the same pointer coming in, and that variable in memory has changed. So this is also a race condition, because the order of execution changes what happens. So that's why we're going to go back and I will comment these out. Oops, I need that one, don't I? And we'll go back to this so that no matter how many times I run it, it's going to always give me the correct answer. It's going to be very consistent on this. Now I could test this out by, for example, putting this in a loop and running it 1,000,000 times and proving that the answer is always sum. That's a fairly, not a proof by any means, but at least it gives you a little bit of confidence that you haven't screwed up a case that comes up reasonably frequently. Okay, and the last thing I wanted to show was, what if we were in a condition that didn't seem like it needed a mutex? So I'm going to change this number of loops down to 100. Just 100. Of course, now when I runs incredibly, now it runs incredibly fast, and we can see here it seems to work all the time. Now, let's actually go through this and get rid of my mutex. So we have the exact same code as before, we're just running it very quickly, a lot less times through. So and we'll see here that it seems to work. And in fact, I could run this quite a few times, and it might seem to work most times. If I ran it 1,000,000 times, though, it might fail very infrequently. So why? Why does this seem to work with a very low count, but when we have a high count on the loops, it fails? Well, here we're only doing it 100 times. This piece of code can run very, very quickly. And in fact, it probably runs inside of, we talk about sort of time slices, even though Linux isn't currently using the time slice idea, but in sort of one time slice or one kick at the can on the processor, we can probably execute all processing of this thread. So this thread will go through in one burst, probably before the other thread actually gets a chance to run. And we have therefore got a lot less of an opportunity to have this synchronization problem crop up. So even though it may seem to work in a number of your test cases, you may have a lingering bug here. When you start running this on multiple processors, maybe it starts to happen 1 in 1,000,000 times. If you start running it on a system that's under heavy load, it may also happen more often if the processors are being switched or multiplexed between threads much more frequently. So even if it's not actually failing for you, it doesn't mean that it won't fail on some system. Which is why synchronization bugs are very, very hard. You want to be incredibly careful anytime you have multiple threads accessing some shared piece of data. Okay, that's all I wanted to mention. Have a look below for some other videos on threads and processes, and have a great day.